I have two problems. One, this doesn't work, but I have an actual real problem, and I'm hoping that everyone here can help me with it a little bit. About, I guess it was 2 years ago, a good friend of mine, Lance Howerson, got up on stage, and he uttered some famous words that have spread throughout our community. Phoenix is not your application. Anybody heard this? Ah, fancy. No one? Anybody heard this? Yeah? Okay, there we go. Sorry, I didn't tell you that crowd participation was going to be somewhat required in this beginning. And this is great. And since then, this is a thing that we've talked about, and that oh, okay. No, this is not a keyboard. All right, sweet. Awesome. This is a thing that we've talked about a lot as a community, and there's been much discussed about it. And Chris got up on stage and talked about how, we had this web directory thing, and we thought that was going to tell people that Phoenix is just an interface to your application, and but it didn't work, so now we had to move it and all this stuff. And I think these are super lauded, important topic. It's just that now I don't know what my application is anymore. And I'm kind of really lost about it. And I went looking all around, and I was like, well, maybe it's Plug, or maybe it's Ecto. And I was looking for other libraries, and I looked at what the most commonly downloaded libraries are on Hex, and saw that it was Poison. So I was like, well, maybe Poison's my application? I don't know anymore. And I'm really adrift here. And so if anybody knows, that would be awesome if you could help me find it out. And luckily, after the keynote this morning, I thought, well, maybe it's the database. Maybe the database is my application. So jury's still out. We're going to find out. And hopefully everybody can help me figure that out. Elixir's awesome. Am I right? And when I say Elixir, I don't just mean the Elixir syntax on top of core Erlang, and I don't mean the beam. I mean everything. I mean the community and the people who are building libraries, people who are maintaining things, and the leaders in the community and everyone who's contributing or writing blog posts or giving talks. Elixir is opening these really, really interesting doors because of its technological capabilities. And it's allowing us to look at programming and looking at solving problems in completely new ways. And so if you're new to the community, welcome. This is an amazing time to be joining because this is early days still. We're still figuring stuff out, and we're still working on what the best practices are. So, in a couple years, we may have those. We may have all decided on the right ways to do things and the best libraries that are out there. But until then, the thing that I want to do and the thing that I want to encourage all of y'all to do is to challenge that. To challenge the status quo and to think differently about how we solve problems. That's really one of the things that Elixir did for me. It showed me a completely new way of thinking about programming. And it wasn't pattern matching, and it wasn't necessarily immutable data or any of these other functional concepts. For me, the thing that changed my career was the process. The idea that the unit of computation in an Erlang application was a single process. And if you wanted state, you needed to use a process. And if you wanted concurrency or fault tolerance or any of these things that we enjoy, you had to use a process. And because of that model of computation, Erlang and Elixir take hard problems and they make them so, so easy. Now, it could also be said that they take easy problems and make them incredibly hard. That's a totally different talk. Or maybe it's several lightning talks, or maybe tonight, if you want to have a beer, I can tell you that talk directly. But in general, they make these things that are hard to approach in other languages, in other runtimes, and other paradigms, so easy. So let's look at a problem and try to illustrate this. So let's say we have a system, and we have an external resource, and we want to limit access to that external resource. And by limit access, I mean that there can only be one reader or writer to that external resource at any given time. Maybe it's a file, maybe it's some other external service that is rate limited in some way. Doesn't really matter. And in fact, what we need to do here is we need to create a lock. Well, the solution for that, at first glance, is pretty easy. Let's just use a process. So we'll create a global lock. It'll start in an unlocked state. And as clients want to interact with it, they can send it messages. For instance, they could lock the process. And then, it'll transition to a lock state, send back an OK. And then when they're done, they can send it an unlocked message. And it'll unlock the process and respond back. This works just as well as soon as you add more clients. Because we have another client, the first client can send it a message, and it can put it into a lock state, send back an OK. And then if another client comes along and tries to get a lock, well, that will error out, and we'll send that error back to the client. And this single process provides a way to linearize all of these other clients. When the first client's done, obviously, it can send back an unlock message. It'll go ahead and unlock it, at which point the next client can go ahead and get a lock. Now, in code, the way this would look is, and this is perhaps not the most efficient way to do this, but it's maybe the most straightforward way. We can use a gen server for this. So we'll have an init callback. That'll set up some initial state. We're just going to put it into an unlock state. And then we want to handle a message. So we want to say if we get a lock message, and we're in an unlock state, transition to a lock state, and save off the client. And that's going to become relevant later because we only want that client to be able to initiate an unlock call. Likewise, if we get a lock message and we're already in a lock state, just go ahead and error. And then it's pretty straightforward to go ahead and do the same thing with unlocks. So for instance, if we get an unlock message and we're in a lock state and it's from the same client, we'll respond with an OK. If it's any other client, we'll return an error. And like I said, this is maybe not the most efficient way to do this, but this is the most, to me anyway, this is an incredibly straightforward and intuitive way to do this, to solve this problem. And I'm not here to tell you that like mutexes are some unsolved problem in computer science, that like other languages don't have the ability to create these kinds of locks. But depending on the runtime that you're in, it can be actually non-trivial to figure out how to get a lock into some sort of like global memory somewhere. You know, depending on the framework you're using or depending on what capabilities your language has. And this leads most people in other paradigms to simply put this state into some sort of external process. So we might use a database for this, or say Redis, or etcd, or God forbid, Zookeeper. And we might put that data somewhere so we can save it off and use it. So this works great for us in Elixir and in Erlang. Right up until we encounter the problem that most companies have, which is, what if we need to run multiple nodes? Most people need to do this. If you want any sort of fault tolerance in your system, you kind of by definition need to run multiple nodes. And so let's see what happens. Well, we'll take our process, stick it inside of a node, and we'll add another one. The problem here is pretty obvious if what we want to do is limit an external resource to a single writer at any given time. Because if you have multiple clients, well, one of them could send a message to this node, it would lock that lock, and another client could send a message to the other node, and that would also get a lock. And this is bad. This is bad because this invalidates the entire thing that we wanted to solve, the entire problem that we had. And when people in Elixir, at least that I've worked with, not at my current job, obviously, but in consulting and some other things, the most common solution that people reach for is, let's just use a global process. We'll just have one, and as long as we have a single process, we'll be fine. So to do this, we'll do something really, really straightforward. Again, maybe this isn't the most elegant solution, but this is the one that's close at hand, and we'll just use the global process registry that's built into Erlang. So we would normally start a process like this. This is how we would start our lock. We would name it lock. Instead of that, we're going to go ahead and just say that this is going to be global. And furthermore, we'll go ahead and say that we'll just need to start these on demand when we need it on any given node. So instead of having two of these, obviously we'll just go ahead and remove this dude. That thing's going to be global. And now, if we get a message from a client to the node that does not contain the lock process, it knows how to forward it on to the node that does. We'll go ahead and lock it. We can respond back to the client, and everything looks really great. The question, of course, becomes, what happens if that node goes away? Well, I don't know. Let's find out. So we'll go ahead and burn that node to the ground, and we'll try this again. We'll take our client, we'll send it a message to this node, and now we realize that the node does not have access to a lock process. There is no lock process in the global process registry anymore because it gets removed when the nodes stop exchanging heartbeats with each other. That's just how it works, sort of by design. And what we might choose to do here is to say, okay, well, let's just go ahead and start a new lock process on this node. No big deal, right? Well, the other one's gone, so it should be totally safe to start this one. So we'll go ahead and fire up a new lock process that can become locked, and we can send a request back to the client. And everything should be working out. But there's a wrinkle to this, which is, what if the node isn't really down? So what I mean by that is, what if, for whatever reason, Amazon has a bad day and somebody LS's the wrong file again, and the network goes down? Well, this is what we would call, in general, a partition in the network. And partitions can happen for all kinds of reasons. The node could actually go down. The network could go down. There's all, if you're running Java, maybe it's garbage collecting for the next 10 years. Like, whatever's going on can cause a partition. Well, if that happens, it's entirely likely that the nodes themselves are partitioned, but they're not partitioned from either client. So this client will send a message to the first node. It'll look, and it'll say, well, I guess it must be down because the process doesn't exist anymore. And it will very happily start a new process for you, as we just saw, and go ahead and get a lock and send that back to the client. The problem is obvious here, which is that that lock still exists. It's still there. And now we have inconsistent data across these two nodes. So this client could come in and also try to request a lock. It could receive that lock, and now we're back into our initial state, which we already decided was bad. So this isn't actually going to work for us. Even more complicated is, what do you do when the partition actually heals? What do you do with your state? How do you reconcile that? So let's say that this partition here finally gets better, doing whatever it is that it does, and now we can talk to both of these nodes again. Well, which one of these pieces of state should win? Which one of them should we keep, and which one of them do we need to discard? This is bad, because this is hard. You have to decide what to do about that in that case. And it opens up all these questions, because maybe you want to decide that the most recent one should win, or rather, like the standard concept of last write wins. Well, how do you determine what was last? You can't use timestamps. Did you guys know that NTP drifts like a lot? Like, it's like totally unreliable. So maybe now you need some sort of like logical clock thing, and this becomes an incredibly hard problem. And that's what leads most people to use the pretty standard solution of, let's just use the database, because this is hard. And so instead, we take this state out of these nodes completely. We just go back to the tried and true method of just stateless applications, and we put this thing in Redis where now we're just beholden to Redis's guarantees, which, depending on who you are, you're comfortable with or not. And that's the way that most people do it. Now, I'm not actually really here to tell you that this is bad. And so please, please do not walk away from this talk thinking that I'm saying that we shouldn't use the database. Listening to the keynote earlier today, I could not agree more with the concepts that Chris was talking about, and just saying that, like, for a lot of things, the database is where you want to put your state. That's not what I'm not interested in telling you all that you're doing it wrong, that goes bad, or that Postgres is, we shouldn't be using it, or whatever. What I am interested in is having alternatives. I am interested in a way to manage state consistently inside of Elixir applications. And what I hope to be able to do is to help provide some tooling around that, but also to provide in this talk a little bit of education about what it means to have a consistent application and the kinds of trade-offs that you're going to make if you want to manage state consistently and not do it using a database, something like that. So before we go any farther, we have to talk about the thing that if you've been around distributed systems at all for any length of time, you've definitely heard of. It's potentially one of the most commonly used buzzwords in distributed systems. And that, of course, is the CAP theorem. I'll go ahead and go through this quickly because it is important. It is useful to talk about because it provides a guideline on the kind of trade-offs that you're going to make. The CAP theorem generally says when a network is partitioned, meaning when nodes can't talk to each other for whatever reason, you can choose to be either available or you can choose to be consistent, but you cannot choose to be both. It's important to note it's important to note this first part, and this is the part that people tend to leave out, which is that it's only when a network is partitioned that you have to make this choice. That's a thing that a lot of people get caught up on, but just keep that in mind as we go forward. It's only when things are actually broken that we have to start making hard choices. And that's a general theme of distributed systems anyway, is that in reality, the only interesting things to talk about are what to do when things aren't working. Because when things are working, well, things are working and it's great. So let's define what these two words mean so that we can talk about them in more specifics. So the first is available. Available basically states that every request receives a response without guarantee that it contains the most recent write. In a different way of putting that is every request is going to get a response back, but the data is going to be wrong or could be wrong. You don't know. And you don't get to know. It's going to be whatever it is. But you did get a response back, and that is what is important. Consistent means that every read receives the most recent write or it errors. And in practical terms, that means at some point, if enough nodes are partitioned from each other, you're just not going to be able to be up anymore in the sense that you're not going to be able to return data anymore. You have to return an error back. But even in a partition, as long as you have a certain subset of nodes available, then you'll still be able to provide consistent data. So you're going to provide the quote-unquote correct data. And we typically talk about these things at these two different paradigms in terms of AP, which is available and partition tolerant, and consistent, or CP, which is consistent and partition tolerant. And like I said before, you cannot choose to be CA, that doesn't mean anything, and you cannot choose to be both. In all reality, most systems don't fall into either one of these buckets, not really. These are guidelines. They're a way to talk about the semantics of a system. In practical systems, most real databases and real stateful systems, they fall on a spectrum on between these two things. So you might be closer to AP, you might be closer to CP. But for our purposes, we're going to just talk about them as black and white. So let's talk about what it means to be available. We're going to set up a new problem, and that problem is that we need to keep track of counts. Right? We have some counter, it's going to always be increasing, and we need to hold on to it. Maybe it's like clicks on a link or ads that have been served to somebody. We need to keep track of how many times that thing happens. So what we'll do is we'll have a process on each node, and that process is going to store additions. It's not actually going to store counts themselves, it's going to store the addition operations that happen on each node. And that is going to allow us to materialize a count when we need to. So we'll initialize both of those to +0. The plus in this case is like a function, right? It's actually like the addition function. We're going to say +0 to whatever you already have. When a client wants to update a count, for instance, like let's say it wants to say, oh, okay, +2 to this thing, we send +2 to the first node, we'll store that off, and then we'll replicate that to the other node. We'll send +2 over, and it can store +2, just like so. If the second client initiates a read to the first node, it'll send that over, and then we can materialize the actual count. So we'll take +0, +2, well, the actual count is 2, so that's what we'll send back, and all that works out. But in the case of a partition, things go a little bit differently. We'll send a new value from the first client to our node. We'll say +3 this time. It'll send it over. It'll store it. And then it'll attempt to replicate this node to the second node. And when it does that, it will fail spectacularly because there's our partition in place. And we won't be able to replicate that just yet. If a second client initiates a read at this point, well, it's still going to get back 2. The data is inconsistent between these two nodes, but it's still serving requests, and that's what we care about. So we're going to send 2 back, and that'll work out. It can also initiate writes. So for instance, it could add its own +5. That would be stored off. And now these things are truly, truly inconsistent with each other for now, while there's a partition in place. Once the partition actually heals, what these nodes can do is then exchange the data between them, and that will eventually replicate all the missing additions across nodes. And now the nodes are consistent with each other again. And traditionally, we refer to this sort of inconsistency during partitions as eventually consistent, because eventually all the data is transferred between both the nodes and everything works out again once there's no partition. The key takeaway here that I really, really want to stress is that sometimes you're going to be wrong. And by sometimes, I mean during a partition. You have no more guarantee that you're going to be right. But that's okay. That's okay for a lot of problems, a lot more problems than you may think. The counts thing is a great example of that. The one that people are maybe more familiar with in this room is Phoenix presence. And this is not meant in any way, shape, or form to slag Phoenix presence, quite the opposite. Because Phoenix presence makes the appropriate trade-off, right? If there's a partition at any time between the nodes that are actually doing the pub sub, well, the data could be wrong. But that's a worthwhile trade-off to make for the problem that Phoenix presence is trying to solve. Because it lowers the operational costs of having to run these different trackers. It lowers the complexity of adding new dynamic nodes to the system. And that makes total sense. And I would say too, as I've worked with lots of people who want to use Phoenix presence for things outside of presence. And if you're in that camp, that's great, do it. But just be aware that that's the trade-off that you're making. And you may or may not be willing to make that trade-off, but it is a trade-off that you have to make. The other conflicting piece of this is that a lot of us, in the kind of work that we do, already have CP solutions in place. And there's certain problems where you just want to have consistent data. For instance, distributed locking in databases. Most of the databases that we use tend to have CP semantics. If you want to do any sort of distributed scheduling and coordination or transactions, those tend to fall into the camp of consistent problems. So I keep using the word consistent, so let's look at a better example of how all that works. So in a consistent system, we might have nodes. They're collaborating together to share data and arrive at the correct results. And these nodes are all working great together, right up until you get a partition. And if you partition off one of the nodes, well, now that node can't collaborate with the remaining nodes, and so we have to shut that node off. That node can no longer accept reads and writes and still provide consistency. So we have to error. We have to return an error and say we can't do that right now because we're partitioned. And if you continue to partition nodes away from each other, eventually the thing will, in fact, just stop responding. It'll stop sending, well, in the sense that it'll stop sending you valid data. It'll start telling you that we can no longer provide consistency, so we can't actually execute your read or your write. This most often happens through a sort of set of algorithms, a category of algorithms, if you will, called consensus. And consensus means what it sounds like, a bunch of computers all working together to arrive at the correct answer, specifically in faulty and partition networks. The most famous of these algorithms, the word that most people have heard, is this word called Paxos. And that was originally published in the late 90s by this guy who is not actually Steven Spielberg, although he looks a lot like it. This is Leslie Lamport, and sort of one of the most important people in distributed systems research. The list of things that he's contributed to the science is kind of mind-boggling. And he wrote this paper about Paxos, and it was this description of how on the island of Paxos they had this way of arriving at consensus over these like faulty networks and stuff. And it was really interesting, and he often like showed up to class dressed as Indiana Jones to explain how this stuff worked together, and no one understood it. No one understood what he was talking about. So a few years later, he published a new paper called Paxos Made Simple, and the problem with that was still nobody could understand it. And so a long time after that, some people decided to write a research paper lovingly titled In Search of an Understandable Consensus Algorithm. And this gave us the technology known as Raft, or I guess I should say the algorithm known as Raft. Raft is the algorithm behind most consistent things that you think of that are out there. So etcd and Console and a ton of others all use Raft under the hood to talk about their data. And for the past, I guess, 5 months now, I have been building it. And there wasn't one for Elixir. I wanted to be able to manage consistent systems in Elixir. That's not fair. There were ones in Elixir. Some of them only ran on a single beam, which I don't know. That's great that somebody built that, but it didn't suit my needs. Or they invented their own log system, which we'll talk about later. But yeah, so this thing is I've been working on it for a while, and now it's sort of somewhat ready for people to see it. So we'll take a look at how it works. So we'll go back to our original problem. We want to limit access to an external resource. We'll take our original code, and with a few simple changes, we can actually modify this to be strongly consistent across multiple nodes. So instead of using a gen server here, we're going to use Raft state machine. Instead, we're going to update our init function, and it's no longer going to return an OK. It's just going to return its initial state. These handle calls become handle write, and we no longer have a from, so we can remove that. And in our reply, the reply tuple there just becomes a two-tuple, where the first part of the tuple is the thing that you want to respond with, and the second part is the state that you want to save off. We can give the same treatment to the rest, so we'll update our next lock, and again, we'll just error if we get a lock message from any other client, and we can do the same things with the unlock calls. We'll just turn those into handle writes as well. Once you actually want to use this thing, there's a little bit of work, but not too much. You simply say Raft start peer. You can give it the module that you want to start, the name of the name that you're going to give it. These do have to be unique across your cluster for reasons that we'll get into. And finally, you set the cluster configuration. So you just tell it, you send a message to S1 and say, hey, S1, S2, and S3 are all in your cluster. And after you've done that, well, now you can write to it. So if you want to write, if you want to send a lock message, you can do that. And it follows the same semantics. If we want to send a second lock message from a different client, that'll all fail. We can, we have to go back through the process of unlocking it from the original client, and then until finally somebody else can use it. So I was originally going to show a video of this, and I thought, to hell with that. Let's just go for it. So I really hope this works. We'll start this up. This is going to start like a little Tmux thing. Maybe, yeah, sweet. All right, so far so good. So over here, where's my mouse? Over here, no, over here. This is our leader, It's already been elected. We'll talk about what elections mean and what leaders mean in just a second. We'll have two other nodes that are part of our cluster, and this over here is our client. So we're going to go ahead and, I don't know if any of that is going to be legible, but let's see. Okay. That's good. That's probably as good as it's going to get. So we can go ahead and we can get the current leader. So we'll ask just an arbitrary node what the leader is for this term. And it's ourselves. That's cool. So we can go ahead and pipe that into Raft.write. We'll send it a message and we'll say lock, and we're going to make up a fictitious client. Just any term works here, and we'll just say C1 is going to be our client. So go ahead and lock it. It's now locked. If we try to send a message to the leader from, let's say, a different client, that should still error. And now, if I haven't totally screwed anything up recently, I should be able to kill, that's S1, so that's the leader right now, and you can see it's writing new commands to the log. I can kill this. An election will take place. It already has. The bottom node there is who won, so that's S3. And we can ask, we'll go back and ask a different node just because we know that S1 is down, so we don't need to wait and watch it time out. We'll ask S1, or S2 rather, who the new leader is. It turns out it's S3, like we said. And now we should be able to, if I can type correctly, unlock C1, and the state should all have been transferred across all the different nodes. We should be consistent. And yes, I can unlock it. And we have consistency across multiple nodes all at the same time, which is, to me, just incredibly exciting. And I can tell all of y'all are just as excited as I am. All right. I can't believe that demo worked. It's awesome. Okay, so how does this actually work under the hood? Well, like I said, it uses a concept called consensus, and along with that, Raft specifically uses leader election and state machine replication. And what it effectively does is it coordinates amongst itself to elect a leader, and the rest of the nodes become followers. The leader accepts all the rights for the system, accepts all the reads and all the writes. Any other node at any point that if you send a message to any other nodes, they will not accept a read or write because they can't. They can't guarantee consistency. Only the leader can do that. So we'll send a message to the leader, and the leader's job is to then replicate this to all of the other followers in the system. So it's going to send a message everywhere. Those followers are going to write that message to their durable log. The log just continues to add entries over and over again. And they're going to write them effectively to disk. When they're done writing it, they send a message back to the leader, and at that point, if a majority, or you'll sometimes maybe hear me call it a quorum, but a majority of the nodes all have replicated the log, that log is safe to be committed. And when it is committed, and only when it is committed, will we respond back to the client and say, hey, yep, here's your new data. Intermittently, the leader sends heartbeats to all of the other nodes in the cluster. It does this on a pretty regular basis, and this is how it maintains its leadership over the rest of the nodes. So as long as those other nodes are getting heartbeats from the leader, they know that node is still the leader and that they should still accept writes and replicate its logs. In the case of a partition, though, they'll fail to receive those heartbeats because the leader node, can no longer talk to them. After a given timeout, which is random between all the followers, each follower has one of those things will time out after not receiving a heartbeat for too long, and it says, hey, we need to start a new election because the leader is gone. And when it does that, it votes for itself and transitions into a candidate state, and then sends a message for votes, or a request vote RPC, to the other nodes in the cluster. And if that follower has not voted in this specific term, then it will grant it its vote and send it back and say, okay. And again, if the candidate receives a majority, I'm glossing over some of the more subtle details here, but if the candidate receives votes from the majority of the cluster, then it promotes itself to leader. It sends messages letting all the other nodes know that it is now the leader, and it can begin to replicate. If the client sends a message to the partitioned leader, the leader that no longer has a quorum, well, it will attempt to send messages to all the other nodes. They will, again, fail spectacularly because they can't reach the other nodes. And eventually, it'll realize that it's partitioned and it needs to transition to a follower state and stop accepting writes or reads. At this point, the client can try the other nodes to figure out who the leader is and to see who to send messages to. So it'll figure out that it's this one. It'll send a message. That node will again replicate. It'll be stored to that follower's log. And when it's done, it comes back and sends it back to the client. And everything is good. When the partition finally heals between all these things, the follower, the original leader from the very beginning of the example, just falls back into the quorum. It gets any of the logs that it missed and it replicates them to its log until it's eventually brought back up into consistency with the rest of the nodes. And that's really the basics of it. It's actually not too tricky to understand, which has been really nice for me, who's kind of a big dummy when it comes to building software. As I said, we have this idea of the log, and the log is used to linearize all of our writes. They're replicated across all the nodes. And for our purposes, we use RocksDB under the hood as our storage engine to actually store all this stuff. And we do that because I don't trust myself to invent my own log and handle anti-corruption and anti-entropy and compaction and all these things. And RocksDB does that for us, which is awesome. It's also, it's obviously a battle-tested library because Facebook has used it in production for a long time, but it's also what underpins CockroachDB and all of their Raft and leader election stuff as well. So we're following well-established paths here. In order to test all this stuff, we use a combination of property tests, and we're slowly writing Jepsen tests. I don't know Clojure, so I'm learning Clojure in order to write Jepsen tests. But hopefully by the end of that, we'll have actually sussed out all of the low-hanging fruit bugs, and that's about when I'll tell you that this is ready for production. Also, if you're not doing property tests, do property tests. It would be impossible to find some of the race conditions, some of the weird interleavings of bugs that happen in these kinds of distributed systems. And property tests are incredibly humbling, but also incredibly useful. So what can we do now? Now that we have this thing, what are we able to do? Well, my plans, the things that I want to do, the things that are on sort of my close timeline, are a key value store. So a key value store you can drop into any Elixir application, and it will be consistent across all nodes in your cluster. Other ideas we've talked about are service discovery, distributed lock management, database transactions even. Anyway, I won't talk about that, but there's interesting things with databases in Erlang we might be able to build transaction processing around, and configuration management. So if you need to do configuration for other processes or other outside services, we'll be able to do that. And we're looking at even being able to do this with systems that are outside of Elixir. So we might be able to provide APIs to other services as opposed to reaching for something else. All of this is part of a new sort of organization that I'm helping start called Tonic. That's where we're putting all these ideas, and what we're trying to really do is build a toolkit for distributed systems stuff in Elixir. So if you want to build stateful systems, we want you to have this toolkit. We've already built a bunch of other things. So we've got implementation of hybrid logical clocks, if you're into that kind of thing. And we've also been doing some pretty interesting work with strongly consistent CQRS and event sourcing, which is interesting. If you want to talk about that, come find me later. The links to all this stuff are here. So if you want to go check out Raft, the Raft implementation, it's there. I'll leave this up for a bit, so if you want to take pictures or whatever, you can. The demo that I just went through is also online. That third thing I bought the domain. It doesn't exist yet as a web page, so don't go there yet. And if you want these slides, they're going to be on SpeakerDeck, or they're already on SpeakerDeck, and I'll tweet them out later as well. If you want to get involved, and please, I really hope that you want to get involved. I hope this piqued your interest. The big thing is much more testing. We want to if we're going to provide consistency, we need to really battle test it. If you're interested in learning about how Jepsen tests work, come and talk to me. We need to do some other work with dynamic node configurations, and there's also a desire from some people to have an LMDB storage adapter. The adapters for the log it already provides a behavior that you can implement, but somebody just needs to go build the adapter for LMDB. There's a handful of other low-hanging fruit that I'd love to talk to you about if you're at all interested in this. And what I hope, my long-term goal is that now, hopefully we can have some alternatives. We can continue to push the boundaries of this stuff, and we can continue to sort of challenge the best practices that maybe we've brought over from other languages, and maybe build some new things and new, very interesting things together. So with that, I'll just say thank you for coming, and I hope you have a great rest of the conference.